Welcome back, students. What you have here is going to be a re-recording of the session of May 19th that was interrupted by bad connections. So in the previous sections, we've talked about electrochemical processes where a spontaneous redox reaction is used to produce energy that is useful to us in the form of electricity. Now we're going to focus on electrolysis. This is the process where you use a spontaneous redox reaction to produce the energy that can help us drive an otherwise non-spontaneous reaction. So that is our topic for now. Electrolysis is the process by which electrical energy is used to cause a non-spontaneous chemical reaction to occur. For example, in nature, many of the metals that we find very useful in our society, aluminum, zinc, iron, they don't exist as such in nature. We only find them in their oxidized states. As we saw in the previous sections, the reduction potentials for these metals are negative. They have negative reduction potentials, meaning that their corresponding ions will not easily reduce. Rather, the metal will oxidize to its ionic form. So how can we get these metals? Well, we need a process that will cause these non-spontaneous redox reactions to occur. For example, let's consider sodium chloride. How do we get metallic sodium when all of the sodium that exists in nature is pretty much in the form of the sodium ion? How do we get chlorine gas when most of the chlorine in nature exists in the form of chloride ions? This is a sketch of what an electrolysis process would look like. In this chamber, we have molten sodium chloride. We have an iron cathode and a carbon anode. Remember, the anode is where oxidation happens. In other words, that is the source of the electrons. Cathode is where reduction happens. That is where the electrons will end up. Now let's look at this if we had it in a lab, if we could do this in a lab, and we had actually a container of molten sodium chloride and simply two electrodes in here. Notice that the anode is still the place where oxidation happens. In this case, the oxidation is chloride ions being converted into chlorine gas. That's a non-spontaneous process. The electrons that are released by that are going to be used on the other side, the cathode, to accomplish reduction. In this case, sodium ions becoming sodium metal. Of course, it'll be in its liquid form. Also a non-spontaneous process. How do we move the electrons in the direction that is opposite to the direction that they would normally move if the reaction were spontaneous? Well, that's what this battery here is for. This battery is generating the potential to essentially pull electrons off of the anode and push them into the cathode. In other words, we're using the spontaneous process in the battery to drive an otherwise non-spontaneous reaction. Notice that the chlorine gas, because it is a gas, it simply bubbles out of the chamber. The liquid sodium that is produced here is actually less dense than the liquid sodium chloride, so it floats and we can siphon it off and then eventually solidify it into plates or blocks or whatever we need. Of course, you know that sodium is very reactive, so we would have to keep it in a moisture-free environment, or else it'll react possibly very violently. All right. Okay, so let's continue here and look at the comparison between a voltaic and an electrolytic cell. On the left, we have a voltaic cell. This is a cell where we are allowing a spontaneous reaction to happen. You remember this. You had the zinc electrode as the anode and the copper electrode as the cathode. Electrons flow from the zinc to the copper electrolyte, the copper 2 solution, so that you can deposit copper over there. And there's your voltmeter, which is simply registering the potential of this cell. Notice that in the voltaic cell, the anode is given the negative sign and the cathode is given the positive. That's because anode being the source of the electrons, we call it the negative electrode. And this is the same thing that happens in a battery, right? The positive end is where the electrons are going to go to. Notice that the electrolytic cell, we don't have a voltmeter, we have an actual voltage source. We have a battery that is providing the voltage to drive this reaction in the opposite direction. Notice that in this case, the cathode is still where reduction happens, and the anode is still where oxidation happens. But in this case, we're forcing the copper metal to oxidize and the zinc ions to get reduced. Notice that because of that, we say the cathode is now going to be the negative one because that is where the electrons are going to go to, right? And we're going to say the anode is the positive side because that is the one that loses electrons. So the big difference between voltaic and electrolytic cells is, number one, that the reaction in an electrolytic cell is a non-spontaneous one that's being forced to happen by an outside source of energy. And secondly, that the negative and positive denominations here are inverted. So in the voltaic cell, the anode is the negative one. In the electrolytic cell, the cathode is going to be the negative one. Let's apply all this to the production of one of the most important metals in our society. And this is aluminum. And let's see why Al is victorious. First of all, aluminum has a very high tensile strength. You can stretch it, like draw it into a wire, but still keeping its strength. At the same time, unlike other very strong metals, it is very malleable. You can roll it, flatten it out into a foil, right? Conductivity, not as good as copper's, 65%, but it's a lot cheaper and lighter. Also, unlike many other metals, aluminum is non-toxic. Now, you might look at the table of reduction potentials and find that aluminum is actually very easily oxidized. But here's the difference between aluminum and other metals. It readily oxidizes in air, but when it does, the oxide forms a very uniform film over the metal underneath and essentially protects the metal underneath from corrosion. This is a process called passivation. Because aluminum can have very powerful reactions in the formation of aluminum oxide, you can use it as a propellant. In other words, if you combust it, it will cause a very rapid expansion of gases, and so you can use it as a propellant. And a very important quality of aluminum is that it can be recycled. So here we have one of those places where they collect the recyclable aluminum, and you can melt it and you can repurify it and use it again. So again, a very valuable metal. So it's interesting to look a little bit about the history of aluminum. Number one, you might not know this, but aluminum is actually the most abundant metal on Earth. Not the most abundant element, but the most abundant metal. Like many other metals, you don't find it in its neutral form. You find it in minerals called ores, principally one called bauxite. It's called that way because it was originally mined from a place in France called Les Baux. It was discovered like in the early 1820s. By the middle of the 19th century, there was a process to purify it, but it was very expensive. I read this in a history note somewhere, and I haven't confirmed it. I'm not a historian, but I'll pass it on to you. It is said that in France, the court of Napoleon III served honored guests with aluminum utensils, while the rest of the people had to settle for gold and silver utensils. In other words, back in the day, aluminum was considered a precious metal, even more valuable than gold or silver. Now, in 1886, young American scientist Charles Hall, about 22 at the time, invented a method for the cheap extraction of aluminum metal. That is Mr. Hall. He was like 22 years old, and he is one of these prodigies that you read about in history. He started college when he was like 16 years old. And as a matter of fact, this process that he discovered, which I think, if I remember correctly, he did it in his parents' shed or something like that. I don't know. Was also discovered in France by another scientist, Paul Héroult. And so sometimes the process is called the Hall-Héroult process. Later on, Hall met with some investors in Pittsburgh, and they formed the Aluminum Company of America, better known as Alcoa. He died in 1914, very, very rich. And you know what he did? He left the vast majority of his fortune to charity. Very, very impressive young man. Okay, let's look at the chemistry of obtaining aluminum. And we, in other places I've taught this class, we have actually a whole unit about metallurgy, the obtaining of minerals and metals from them. But we'll talk a little bit just about aluminum here, just for example. First of all, remember that we said that aluminum is obtained from a mineral called bauxite. Essentially what it is an aluminum oxide that is bound with water molecules. And the first step in the process involves heating it in very hot sodium hydroxide. What this does is it removes other minerals like silica and silicates, and converts aluminum to a form that has a beautiful name, the aluminate ion. I love that word. The next step in the process, and again, I'm simplifying this, but the next main step in the process involves, again, precipitating the aluminates with acid in the form of aluminum hydroxide. An alternative to this is to acidify using carbon dioxide and then precipitating the hydrated aluminum hydroxide. Now, these hydroxides are going to be reheated to generate a semi-pure anhydrous aluminum oxide, which is called corundum. And corundum is the one product that is going to be subjected then to electrolysis. So this is now the purified aluminum oxide. You see Al2O3, you see it here. That is what is called corundum. And this is what is going to be used for electrolysis. So in a typical cell, what they do is they put this aluminum oxide or corundum in a mixture with molten cryolite. Cryolite is also a compound that is made with sodium, aluminum, and fluorine. It's a complex type of compound, and at very high temperatures it dissolves the corundum, the aluminum oxide here. Notice that carbon is used as both anodes and cathodes in this process. Here is another sketch of it, so you can see how as aluminum is produced, it sinks to the bottom, and you can therefore just drain it out of the bottom of the cell. Let's look at the reactions that are happening in here. Okay, at the anode where oxidation happens, what is getting oxidized is actually the oxides present in the aluminum oxide back to oxygen gas, which of course will bubble out, and that releases electrons that are then used at the cathode to reduce the aluminum to aluminum liquid metal. Like I said, I am simplifying these reactions. There are some intermediate steps that involve the use of the actual carbon in the anodes and cathodes. So please understand that this is kind of a sketch here. Let's look at the final reaction here. All right. The final reaction here would essentially be the aluminum oxide converting into aluminum in its liquid form, and then oxygen gas, which bubbles out of the mixture. So very interesting process. Let me give you a few moments to download that. All right. So electrolysis, essentially illustrated here, is also one of the processes that are used in the production of many other metals. Another very important metal, of course, is iron, which we obtain in the form of steel, which is really not pure iron. It's actually iron mixed with other things like carbon, sometimes maybe nickel, chromium, other things. So you can read about that in your textbook about how the production of steel is carried out. Let's do a little practice ourselves. This is the way that electrolysis problems are handled, okay? Remember that in electrolysis, you are forcing current into a system in order to drive an otherwise non-spontaneous reaction. Don't forget that current, or amperage or amperes, is the charge passing through a point in a given amount of time, specifically in a second. And don't forget that the Faraday constant is that 1 mole of electrons is 96,500 coulombs of charge. So this is the flow chart that we're going to follow. Typically in an electrolysis problem, there are going to be like maybe 3, maybe 4 different variables. You will be given 3 of them and asked to find the 4th. All right. So typically the flow chart goes like this. You're going to be providing a current, and you're going to be given the amperes of current and the time. And of course, remember that if you have the current and you have the time, according to this equation that we have here, we can find what is the actual charge in coulombs. That's the second step over here. Divided by Faraday's constant, we can get the number of moles of electrons that are being transferred in the process. If we now go to the half-cell reaction, where the metal of interest, or the, I guess, the product of interest is being produced, we can calculate then, based on the number of moles of electrons and the stoichiometry of that half-cell reaction, how many moles of substance have been produced. And if we have the molar mass of the substance, for example, if it's a metal like aluminum or nickel or whatever, we can calculate how many grams of product we got. Don't forget that we also use electrolysis for producing gases like chlorine that are not easily found, or really not found in nature. And so in that case, we would use the moles of substance and the ideal gas equation, knowing the temperature and knowing the pressure, and we can calculate how many liters of the gas we can get. So let's do a practice problem. How much calcium will be produced in an electrolytic cell of molten calcium chloride if a current of 0.452 amperes is passed through the cell for 1.5 hours? Remember the flow chart we just discussed, right? And notice that we're starting, they're giving us the current and they're giving us the time. So we're going to follow this flow chart just like it goes in there. All right. Now we had to make some initial equations here, or reactions, right? Because if we start with calcium chloride and we're being asked to produce calcium, that means that what's happening to the chloride ions? Well, the chloride ions would have to be converted to chlorine gas. And that's an oxidation, so that's happening at the anode. And at the cathode is where the calcium ions are going to get reduced to calcium metal. So our next reaction would involve calcium chloride, just like the formula says, being converted to calcium metal and chlorine gas. What's important about doing this process is identifying the number of electrons that are required for every mole of calcium. That's what's important here. 2 moles of electrons are required to produce 1 mole of calcium. So let's see if the current is 0.452 amperes and is running for 1.5 hours. How many moles of calcium can we get? So remember, 1 ampere is 1 coulomb per second, and we're running it for 1.5 hours. We don't always remember this formula, but 1 hour has 60 minutes, 1 minute has 60 seconds. That means that there are 3,600 seconds in 1 hour, and we're running this cell for 1.5 hours. Then we have to remember that since the equation of interest here is the relationship, the stoichiometric relationship between the moles of electrons and the moles of calcium, we know that 1 mole of electrons is 96,500 coulombs, and 1 mole of calcium will be produced for every 2 moles of electrons that are being transferred in the reaction by this electrolytic cell. It seems like a long journey here, but let's make sure all the units cancel out. So hours cancel with hours. Seconds cancel with seconds. Coulombs in the current cancel out with coulombs in Faraday's constant. And finally, moles of electrons in Faraday's constant cancel out the moles of electrons given by the stoichiometry of our half reaction. So in the end, we're going to have units of moles of calcium. Let's do all these calculations, put them in the calculator, and we get 0.0126 moles of calcium. I think the person who did this essentially assumed that the current here was kind of like the determining factor in terms of sig figs, and so they just considered that there's 3 sig figs there, 3 sig figs here. We'll leave it at that, no problem. It's not a big deal right now. Calcium, of course, we can find its molar mass in the periodic table, and we found that, again, in the end, now doing all of the rounding based on the 2 sig figs here, we get 0.50 grams of calcium, or 500 milligrams of calcium after a 1.5 hour process. In the activity you guys are going to be doing this week in your dry lab on electrochemistry, this is part 2 of this lab, you'll have a chance to do some problem solving with electrolytic cells, but they'll be with aluminum. So hopefully this practice exercise here will prepare you for that. There are some other applications of electrolysis, not merely to recover metals, but how about, for example, electroplating jewelry? Many of products that you find out there are not pure silver or pure gold. They actually just have a coat of the precious metal on top of an otherwise regular, cheap metal. So for example, let's say I have a spoon in here and I want to electroplate silver on it. Notice that the electrolytic cell here would require an anode of pure metal, so I would have to have pure silver in there. As the voltage source, the battery, draws electrons from there, right over here, that releases silver ions, which will travel through the electrolyte solution, which could be made of different things. And as the electrons arrive on the other side, they will charge the spoon and allow the silver ions to deposit as silver on top of that spoon, giving you essentially an electroplated, silver spoon, but it's not pure silver, it's just coated with it. You can do the same thing with gold, for example, maybe with platinum also. All right, let's talk about another process that involves the moving of electrons, another electrochemical process. So far, we've seen generating electricity from spontaneous redox reactions. We've seen producing otherwise non-spontaneous reactions to occur by the use of electrical energy. We've seen here electroplating. These are all good things, but there is such a thing as bad redox, and that is what we call corrosion. So corrosion is essentially the deterioration of a metal due to an electrochemical process. Let's say that we looked at the head of a nail or screw that has been left out, in the garage and the tool shed too long. It's been exposed to air and moisture, and what is happening is you're accumulating rust in here. Of course, if you kind of like scrape off the rust with a metal brush, you'll see that the metal underneath is corroded. It's lost its shape there. This process is, somewhat more complicated than what I'm showing here perhaps, but essentially notice that what you have here is an electrochemical cell. At the cathode, you have oxygen being essentially reduced to water. This is something that in moist conditions, particularly on a surface that is moist, with carbon dioxide dissolving in it and making it slightly acidic, we saw this in previous units, the oxygen were very, readily reduced into water with a potential of 1.23 volts. I'm talking about, what's happening here at what we're calling the cathode. What is the source of those electrons? Well, again, you have on the left side of the picture, but it's all kind of mixed in, the same moisture in there and the same acidity will cause iron to get oxidized into iron 2 ions, and they can even further get oxidized to iron 3 ions. The point here is that those ions will dissolve in the water and create these different kinds of iron oxides. That is what rust is. And the majority of iron oxides, particularly I think the iron 3 oxide, has like a reddish orange color, which explains why rust is typically has that kind of like either orangey or brown kind of color. So this is very bad because we do rely on many structures and many things where iron in the form of steel needs to be protected from corrosion. And not just iron, but many other types of metals. So one way of preventing corrosion is by coating the metal surface so that it keeps it away from any corrosive chemicals in the environment. I mean, one of them is just simply to paint the steel structure, the iron structure with some, water resistant paint. But another interesting process is something called cathodic protection. So essentially what this is you take your metal you're trying to protect and you attach to it a more reactive and cheaper metal. We call this the sacrificial electrode. I'm showing you here a box of galvanized nails. And what they've done with galvanized nail is essentially they have a layer of zinc that has been electroplated onto them. And what that does is the zinc will oxidize more readily than the iron does. But when it oxidizes, it passivates. Remember that word? It means it forms a thin layer of the zinc oxide, which unlike rust, which as you can see in this picture here, is kind of like a very uneven, very kind of like, porous type of material, the zinc oxide is not. It's almost like a skin that forms on top of the iron, and it protects the underlying metal from further corrosion. Chromium can do the similar thing, and it's used for protecting steel. Aluminum will do the same thing, and that's why we can use aluminum in soda cans because it oxidizes, but it forms this layer that protects the rest of the metal from corrosion. When my son, before my son graduated from college, he's an industrial, he is a mechanical engineer, I'm sorry. He did an internship with the Irvine Ranch Water District, and one of their jobs was to go out on the field and inspect pipes and water storage tanks. And we talked about how they use cathodic protection there also. So to protect, let's say, pipes that are underground or water storage tanks that are underground or even water storage tanks that are above ground, what they do is they use cathodic protection. To prevent these tanks from rusting, they put a sacrificial electrode. They essentially connect them to another metal that will oxidize more readily. Uh, one of the metals they use is magnesium. Another one they use is zinc. And so what happens is the electrons are drawn into that sacrificial electrode instead of getting drawn out of the iron and oxidizing the iron. The sacrificial electrode is the one that gets oxidized. I wanted to close out with an interesting little feature here. I'm sorry. I hope this never happens to you, but yes, this is what is called a breathalyzer. It's an instrument that is used to quickly detect the presence of alcohol in the breath of a suspect, just in case they need to be given a DUI. And let's look at the chemistry behind this. So essentially, the chemistry behind it has to do with this reaction here. The first reactant you see here, CH3CH2OH, that's actually ethanol, that's the alcohol. And then what you do is in your analyzer, you have potassium dichromate. We have seen this substance before. It has kind of like a reddish, orangish kind of color. And in the presence of an acidic solution, what it does is it oxidizes the alcohol into acetic acid. As a result, the dichromate is converted into a chromium 3 sulfate, which actually has a greenish kind of color. And so what the machine does, it registers the change in absorption pattern of the light from the original potassium dichromate into the product, and it has a detector that converts the amount of light absorbed of the proper wavelength into a meter that then converts it into a percent of alcohol in the breath. So that's kind of like how a breathalyzer works. Although I believe that recently they've changed and now they may be using a different kind of reaction nowadays, but this is the original design of breathalyzers. All right. I think if I go through the rest of this just to show you how the chromium is getting reduced here, that was all I wanted to show here. Thank you so much for your attention here. This is the end of our unit on electrochemistry. Please make sure that you read the rest of the material in your text and that you go back to our study guide so you can see if there's anything you need to read from the text that we didn't cover that might be included in the test. Please try to do a lot of practice exercises because this upcoming exam is pretty heavy on the math, as some of you have pointed out to me in previous sessions. Thank you so much, and I hope to see you soon. Take care.